Welcome to Plutus IAS. So in last class we talked about LTA, which is lead tetraacetate, and now today we are moving further. So today we'll be discussing how LTA is used as a decarboxylating agent for removing CO2 from your compounds and to form alkenes, and also we'll be looking forward how LTA is used for the formation of lactone. Now, although the decarboxylation and cyclisation are subjected to different conditions, for example, if you are having a normal carboxylic acid, no matter whichever type it is, if you are using LTA with it, it will always give you an alkene. Okay. While for other cases, whenever if you are having LTA which has a nearby double bond to it, in such a case you will find that it will give you a lactone rather than giving you an alkene. So today we will be discussing these two different uses for LTA along with the mechanism for it. So first, let's try to form an alkene. So let's suppose you are having a carboxylic acid of this type, and this has alpha and beta carbon, CH, and let's say I don't need the substitution right here, so it can work anyway. So in this case, if I take LTA, in which I'll take PbOAC whole thrice, keeping one OAC above, I see what? I see in this case, when acetate leave as a leaving group, the oxygen will attack the lead, forming lead-oxygen bond, which looks like this. Oxygen. This will give you oxygen, hydrogen, positively charged, lead. This will give you PbOAC whole thrice in this case. Now, in next case, this acetate can be made like this. At least one alpha hydrogen. There should be one hydrogen for the formation of alkene. This will be 2, and one acetate can be written like this: C double bond O and CH3. Now what happens is, oxygen will take up electrons. In this case, the oxygen will take electrons from the hydrogen, removing H+, which will form your acetic acid, and the positive charge gets removed. While further in the step, what happens? Now, this acetate will leave as a leaving group. In this case, then the lead will try to complete its electron by taking away the electrons from the lead-oxygen bond. And for this case, the carbon will transfer its electron density to this side, which will remove the products which are CO2 and PbOAC whole twice. Now, after transferring of electron, we'll have a carbocation here. This carbocation, the hydrogen will transfer the electrons and the oxygen will attack this hydrogen, removing another mole of acetic acid and giving us alkene that we want. Now, for this decarboxylation, it is always necessary that you should have at least one hydrogen on your beta carbon. This will help in the formation of alkene. Now, this was the first case where we talked about decarboxylation. No matter whether you have a cyclic compound, acyclic compound, the result will always be same. But for the next set, if I'm taking a double bond, for example, let's say this is a compound and it has COOH here. Wait. It has COOH at this position, and I use LTA over it, and it gives me this compound. This will have OAC and lactone formed here. Now, we need to discuss how this lactone, wait, the positions are wrong. Now, we need to write the mechanism for it, how this is occurring. lectron. Now the mechanism will go like this. So wait. So for the mechanism, we'll take this compound just like the previous case, carboxylic acid, hydrogen, PbOAC whole thrice, 1 OAC here, which will remove here. Oxygen will take the electron density from hydrogen and attack the lead, forming C double bond O, O, PbO, AC whole twice and 1 OAC here. Now in this case, what will happen? In this case, when the acetate groups leave as the leaving group and the lead withdraws the electron from the oxygen. Now, instead of breaking the carbon-carbon bond, this compound, the double bond attack nucleophilically on the electrophilic oxygen. And this leads to the formation of a carbocation will be generated here. This will look like this, and you have got your compound, which is your lectron. And this positive charge carbocation, the OAC that you have removed in the step, will attack this position and give you our final product as expected, a lactone. So this is how LTA is used for decarboxylation and for cyclisation purpose to get lactone. The condition is, if you are having a double bond in the carboxylic compound, it will form a lactone. And the condition also arises that the double bond should be at gamma delta carbon. For example, this is your alpha carbon, that's your beta, that's your gamma, and that's your delta. That means for the formation of lactone, this particular condition that your compound should definitely have a gamma delta bond, which will further ease up the cyclisation process. So I hope now you have understood how LTA works for these two purposes, and we'll see you in the next class then. Thank you for joining us.